So today's topic is about how to find local maximum value and local minimum value, or absolute maximum value, absolute minimum value. Okay. So what's the difference between local and absolute maximum value? Local maximum value just needed to look at the local behavior of the graph. Okay. And absolute maximum value means over the whole period, okay, whole interval. What is the maximum value of the function? Okay. Before we do that, let's introduce the concept, the critical number. Okay. So we assume that the function defined on the interval somewhere, and the C is a number. C is an interior point. Okay. So we assume that let f(x) be a function on some interval I, and the C is an interior number. Okay, inside the I. It's not the boundary point, end point. Okay, interval could be, could be an open interval, could be a one side closed, other side open, for example, right? So just a number inside the interval. Okay, we say that C is called a critical number if one of the two cases happens. If f prime C does not exist, or f prime C equals 0. Okay. So either doesn't exist or equal to 0. Now, what does it mean doesn't exist? How does the graph look like if the limit does exist? The graph looks like that. Picture like that. This is a graph. Okay, exists. The derivative exists, could be smooth. Okay, could be like this point, could be like this point. Okay, yeah. So those are the pictures. Okay. So that means the left-hand limit does not equal to the right-hand limit. Remember, the limit is good. The derivative at that particular point is going to be the limit, right? Sx approaches C, and x minus C of fx minus f of C. So that is the limit, right? And if there's a cusp, it's the graph, this point is cusp, then you don't have the limit. Okay, the limit doesn't exist, the derivative doesn't exist. It's also called the critical numbers of the function. Why we want to study critical numbers? Okay, the critical numbers, because we have the following important theorem. Okay, says that if the function has a local maximum value or minimum value, or minimum value at C, okay, then C is a critical number. Okay. Now local maximum value means like that. Means local maximum value, right? If f of C is a local maximum value, which means how does it look like the graph? The graph looks like that. This is local maximum value, and it could be like that. Okay. So this is a point. Here's a C. Here's another picture. Okay. It's in the XY coordinate system. Okay. The first picture, the derivative should be equal to 0 at that particular point if it has a local maximum value. This is the highest point. You can put a horizontal tangent line there. Okay, tangent line is horizontal means the derivative is 0. The slope is a derivative, right? And here the derivative does not exist. So in either case, the number C is a critical number. So it's easy to understand from the picture. Okay. So why this part in term is important? Because it's very hard to find local maximum value, over the whole interval, because you have to check the value of the function at every point. So now we just need to look for the few candidates, right? And then you can determine the local maximum value, local minimum value. Okay. So let's look at some example. Okay. F of x equals x plus 1 of x. X is greater than 0. So the interval here is a whole interval from 0 to infinity, right? Okay. We can actually even find not only just local minimum value, we can now even find absolute minimum value. Okay. So let's look at this graph. Okay. We know that the function as x approaches 0 from the positive side, it's determined by the second term, 1 of x, which is going to be 0 plus infinity, right? It's going to be positive infinity. We also look at the value, the limit of the function as x approaches infinity. Then the first term determines the value, which is positive infinity. So if we draw the graph, it goes like that, right? Somewhere, maybe they're shaking here. I don't know. Let's at least both ends going to positive infinity. So somewhere in the middle, somewhere there should be lowest point. Okay, there is the lowest point. So let's find out. So you already know the function has a local minimum value somewhere. Okay, in the interval. That number must be critical number. So let's find out. See, that otherwise, how do you find the minimum value of this function, right? The smallest, the least value. So you look at the derivative, you get 1 minus 1 of x squared, find the derivative. And this should be equal to 0, you solve that. And you find out x squared is going to be 1, x is going to be positive, because we only consider positive x. So at point, this the only, yes. So 1 is the unique critical number. Okay. Now what we can say? If the function has a local maximum value, minimum value, somewhere in the interval, then that number must be critical number. That's one side. Okay, that's the theorem. On the other side, you look at this function. There's only one critical number. Then what you can say? So the function has a local. Actually, if you look at the whole picture here, the function has first of all, you can just say it has a local. We don't know. If we don't draw the graph, you can only say it has a local maximum or minimum value at x equals 1, right? But since we already know the graph, two ends goes to positive infinity, so then you can conclude that this not only just local minimum value, it has absolute minimum value. So the function has the smallest value, right? Has a absolute minimum value at x equals 1, and the value is going to be 1 plus 1 over 1, which is 2. Okay, this is the smallest value. In other words, from here you can conclude that x plus 1 of x is always greater than equal to 2 for any positive x, right? Because 2 is going to be the smallest value. Actually, this can be proved directly without using calculus. How to do that? Okay, x plus 1 of x minus 2 is going to be square of x minus 1 over square x squared. Okay, and that is actually always going to be greater than equal to 0, guaranteed. right? For any x greater than 0, right? You just check to verify this identity, then greater than equal to 0, then it's clear that, and when it's going to be 0, when x equals 1, okay? And the equality holds if and only if square x equals 1 over square x, which means x equals 1, okay? So without using calculus, you still can jump to this conclusion, but we're not always lucky. You know, we will see the power of the calculus to solve the problem. For this specific function, without using calculus, I still can tell. First of all, the value of the function must be greater than or equal to 2 always, and equal to 2 when x equals 1. Only when x equals 1. Without using calculus, just using elementary mathematics, which elementary means any mathematics, high school, middle school. Okay? Because everybody know, if I tell them this is true, everybody can verify that. Okay? And then squares never be negative, so greater than or equal to 0. All right. All right, so did I give you the definition of the absolute maximum? Absolute maximum value, yeah, absolute minimum value. If you know what is the definition of absolute minimum value, then you can, same idea, you can define the absolute maximum value. Okay, here's the definition of absolute maximum value. Okay, so if f of c is always greater than or equal to f of x for any x in the interval, then we say that f of c is absolute maximum value. Okay, and here c should be and c is in the interval. Okay, otherwise we don't call it. It's not even the value of the function, right? Okay, so here's the example. F of x equals x squared. X is between 0, greater than 0, less than 1. Okay. Now on this interval, okay, the function has absolute minimum value. Okay, f of 0 is going to be the absolute minimum value of f on the interval I, over the interval I. Okay, but since 1 is not, f of 1 is not defined, it's undefined. Okay, because we only define the function from the closed interval from 0 to 1, but 0 is included, but 1 is not included. So you cannot say f of 1 is absolute maximum value. Okay, we know that it's always greater than, less than, equal to 1. Okay, for any x. Okay, and we also know that the limit of the value of the function is going to be 1. But 1 is not the absolute maximum. So this is a concept, right? 1 is not the absolute maximum value of the function on the interval. Okay, because since it's not the value of the function, that's it. Since 1 is not the value of f at any number. Okay. Okay. So that's the reason, because it's not value. How can you say it's the maximum value of the function? But you can also say that 1 is the least upper bound of the function. You can say that. Yeah, but we can say the least upper bound. Okay, we can say that 1 is the least upper bound of f. Okay, why you can say that? Because any number greater than or equal to 1 is the upper bound of f. 1 is the least upper bound. Okay, and any number smaller than 1 cannot be the upper bound of f, because f is getting close to 1. So that's why 1 is the least upper bound. So that's a, so yeah, you have to be familiar with this concept. Okay, so I cannot say, so we can say that f does not have absolute maximum value. Okay, although 1 is the least upper bound of the function. But yeah, think about the next problem. This is going to be 1 plus x plus 1 squared. X is between -2 and 5. Okay, let's draw the graph first. And from the graph, you can tell. Right? It goes like that. This is not included, this is included. Okay, I can tell that. Yeah, I hope you understand, okay, my statement. Step 1. F, step 1, F does not have the absolute maximum value. Okay, this is a point 5. What is the value of that point? 37. Okay, this is going to be when x equals -2. It's going to be -2 and 2. Okay, and this is going to be -1 and 1. Okay, it's parabola. So 37 is not going to be the maximum, absolute maximum value, because the function never be, the value of function never be 37. Okay, so the function never be 37 for any x in the interval. Alright, so 37 is not absolute maximum value. It's the value of the function at all. Okay. Second, f2 -2 equals 2 is a local maximum value. Why? It's locally, it has maximum value. It's very simple. If we look at it, just look at the picture, we don't need to look at the group picture. We just look at the local picture, right? And then here's an arbitrary x, and clearly f of x is less than or equal to f of -2, which is 2. For x close to -2, right? Yeah, it's below that. Clear, right? So that's why 2 is the local maximum value of the function. Okay, third, f of -1, which is going to be 1, is not only the local minimum value, it's the absolute minimum value of the function over that interval. Right, from the picture. That's the lowest point. Now, actually, how can I get a -1? If the function is complicated, how can I? -1 is a critical number. Okay, what we did here is, yeah, let's look at this. Okay, we calculate f of x. It's 1 plus x squared plus 2x plus 2, right? Plus 1. So it's going to be x squared plus 2x plus 2. So you find the derivative. It's 2x plus 2. You set this to be 0. X is going to be -1. So this is a critical number. So there's possibility there is a 1 local maximum value somewhere. Okay. This is the function has a local minimum value at that point. But it's not a, this is not an equivalent. If it sees the critical number, does not mean the function has an absolute maximum value or a local minimum value or local maximum value. Okay, It's not necessary. We only said that if the function has local maximum minimum value at C, that C must be created number. Conversely, it's not true. Okay. So yeah, here the statement is that if this one has a local maximum or minimum value at C, implies C is a critical number, right? But conversely, this is not true. Okay, it's not guaranteed the value of the function is a local maximum or local minimum value. Here's the example. F of x equals x cubed. Okay. Let's look at the critical numbers. The derivative is going to be 2x, 3x squared is to 0, right? So x equals 0. So 0 is a critical number. The only critical number of f on the interval, on this interval. Okay. Does the function have local maximum value? Does the function have local minimum value at 0? Answer is no. Because we already know the picture. The picture goes like that. Okay, and locally, the value function is smaller than, yeah. So f of 0 is 0, right? So clearly, f of x is less than f of 0. For x less than 0, then if x is greater than 0. Okay, so f of 0 is not going to be local minimum value. Maybe only one side of the local maximum, but it's not. Yeah, by definition, it has a local maximum value. It is a local maximum value, then for x close to 0, f of x should be less than or equal to f of 0. Okay, so it's not a local maximum value, local minimum value, but 0 is still a critical number. Okay, now let's take a look at some more complicated problems. F of x equals 2x cubed minus 3x squared minus 36x, and no restriction on x. So that means x is between -3 and negative infinity, positive infinity. Okay. It's hard to draw the graph. I want to find out the local maximum value, local minimum value, if any. And does it have a absolute maximum value, absolute minimum value? Maybe not. Okay. It's clear that the function x approaches the positive infinity. The leading term is 2x cubed. This is positive infinity. When x approaches negative, it goes to negative infinity. So if you draw the graph, it goes like that. In the middle, I don't know. Okay? Because when x approaches negative infinity, f of x approaches negative infinity. Okay? So going down this direction. Okay? So in the middle, maybe like that. Okay? Who knows? Okay? Maybe it's possible. It's it is always increasing, like a special case y equals x cubed. Okay, so there's possibility you have a one local maximum value, one local minimum. Maybe there are many local maximum value. All right, so let's take a look at f, the derivative. Okay, the derivative is going to be 6x squared minus 6x minus 36. So take 6x. Okay, so it's going to be 0. X equals -2, x equals 3, -2, here 3. Okay, I think from the picture, the function has a local maximum value at -2. Why not local minimum value? It's hard to draw the picture if this is the local minimum value. Okay, it must be like that, up and down. Okay, so no choice. Yeah. So f of a -2 is a local maximum value. Okay, and f of 3, you get local minimum value, and it's from the picture you can tell that. Yeah, why not f of -2 is local maximum value? If it's local minimum value, if it's local minimum value, one side is going on, right? This is a go to negative infinity. Then you have to go down, right? If here's -2, then there is another point to local maximum point here, and that is not possible, right? So that's the reason this is impossible. This picture is impossible. The function does not have a local minimum value at -2. If it has, then you have another number on the left side of -2. The function has local maximum value because it's going up, then you go down first a little bit in order to make that one a local minimum point. So then there's a local maximum. So it's clear that it must be local maximum value, f of -2. Okay. Now, we're going to spend more time to determine whether the value of the function has local maximum and local minimum if C is a critical number. Okay, it's not easy to do that at this moment. Okay, we're going to study this later. Okay, how to determine f of C is a local maximum or local minimum if C is a critical number, right? Here's a question. Okay, if C is a critical number, and so for this particular function, I can tell from the graph, but sometimes the function is complicated. It's not easy to see. Okay, how to determine the local behavior of the function at C. How about like that? Okay, local behavior. Yeah, there are only two possibilities, like this, like that, or like this. Okay, it's critical number, but we assume the function is smooth. Right? This is also tangent the line. That point is horizontal, 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 right? Just three cases. How do you determine local behavior? Okay, we are not going to study this right now. What we have is the following intrinsic theorem. We let f be continuous on a closed interval. Okay. Then f must have the absolute maximum value or a minimum value at some c in the interval. And this c could be an endpoint. Okay. So this c, if we inside the interval, then c must be a critical number. But it's possible C could be critical number inside interval or could be an endpoint. Then you do so many candidates here: critical numbers, endpoints, right? Okay. So here's a question. Okay, you have a function. Okay, it's defined on the interval from 0 to 4. Let's see whether the function has a local, I'm going to find out the absolute maximum value, absolute minimum value. Well, according to above theorem, the function, if the function is continuous, so must have an absolute maximum minimum value somewhere at C in the interval. So that C is the endpoint or critical number. So what do you have to do? Find the critical numbers. There are only few candidates for the value of C, right? At which the function has a local maximum value or local minimum value. Absolute maximum, absolute minimum value. Okay. So why this is true? Because of if the function is continuous, that means the graph is not broken. If the graph is not broken, from the graph you can tell if there's absolute minimum value here and absolute maximum value here, even at the two endpoints. All right, so what I have to do, just to find the derivative. And you set it to be 0. So x squared is 54 over 6, it's going to be 9. X is going to be plus minus 3. Since our interval is from 0 to 4, then that implies x should be equal to 3. Is the only critical number inside the interval. Okay. So we find the critical number. That's our candidate. Okay, for the function to have a maximum value, a minimum value, right? Okay. So if according to the theorem, the function must have an absolute value, then it could be at the endpoint, it could be at critical number. Okay, but must be in one of the cases. So what we could do is we just need to evaluate the function at the two endpoints, f of 0. So that's going to be 5, because 5 plus 54 times 0 plus minus 2 times 0 squared equals 5. F of 4, 5 plus 54 times 4 minus 2 times 4 cubed. Yeah, you can yeah, we can simplify. That will be, I think again 93. It's very large number. Okay, then we have to look at the value of the endpoints. It's 5 plus 54 times 3 minus 2 times 3 cubed. And the answer is going to be 130. So we don't know how to draw the graph, but it's okay. We see that you have 3 values, right? If the function has a maximum value, the maximum value must be, absolute maximum must be one of them, okay? Because if f of c is the maximum value, absolute maximum value, then c must be either the critical number inside or the endpoint, right? So clearly c should be equal to 3. So at 3 is at 3 the function has absolute maximum value. The minimum value is 0, right? F of 0 actually is absolute minimum value. Okay, one of the endpoint. If you draw the graph, it goes like that. I think we should learn a little bit about graphing before we continue, so we can tell how many critical numbers there are and whether the function has a local maximum or local minimum value. Okay, we have two typical graphs. This is y equals x cubed, right? Another one is y equals negative x cubed. But if you add some terms, then it disturbs the graph because those addition terms. You still, when x sufficient large, is still the same, but the graph will up down twisted somewhere. Okay, but for x sufficient large or sufficient negative large, then graph approaches the graph of y equals x cubed. Okay, but this part does not play loose when x sufficient absolute value of x sufficient large. So graph of a polynomial degree 3 must look like that. And the local maximum point must be on the left side of the local minimum point. Okay, just like a parabola, it has a certain shape. And the same here, if it's negative x cubed, then if we consider a function, okay, like that, and the graph looks like that. Okay. So that's why we have that picture. It's not surprised. Okay, this is a 5. When x equals 3, 113. When x equals 4, that could be 93. Y value is 93. Okay, so we consider this piece of graph. All right. But if the disturbance is small, maybe minus 3x, for example. Okay. No x squared in the function, just x. Okay. I know the graph. How does it look like? The graph looks like that. Possibly, right? But clearly, when x equals 0, the y value is also going to be 0. So the graph passing through the origin. So you have to modify a little bit. Okay, I'm going to modify this. Give me x squared minus 3. I can tell that this graph passes through 2 points. Okay, without finding the derivative, I can tell I can give you some rough estimate. Okay, so that means if you set this to be 0, x equals 0, x equals plus minus square 3. So how does the graph look like? I'm going to erase this part. Okay, the graph passing through this point, passing through this point, passing through this point, right? I know the graph looks like that, so it must be like that. Okay. So you can tell the graph has local maximum value somewhere, local minimum value somewhere. Let's find out. So x sorry, that's already derivative. Yes, this is a derivative. So 3x squared minus 3 equals 0. So x squared equals 1, x equals plus minus 1. Okay, those are the two critical numbers. And clearly from the graph, I can tell that f negative 1 is a local maximal value of the function. F1 is a local minimum value of the function. Okay, you can calculate what is f of negative 1. F of negative 1 is going to be negative plus 3. Negative plus 3 is negative positive 2. Other one is negative 2. All right, so let's take a look at the next function. Okay, this is on the interval. Now make sure the function is defined. It's not broken. Otherwise, you cannot find the theorem. Okay, if the function is continuous on this interval, then this function must have absolute maximum value, absolute minimum value. Okay. X squared minus x plus 1, can it be 0 or not? I look at trying to solve this equation. If the equation has no solution, it's always positive. Okay, so b squared minus 4ac, remember quadratic formula. It's negative 1 squared minus 4 times 1, it's going to be negative 3, it's less than 0. So it does not have any zeros. If it doesn't have any zero, it's positive somewhere, then it's positive everywhere. Okay, so this implies x squared minus x plus 1 is always positive for any x. So yeah, so don't worry about the denominator. Right? In order to find absolute maximum value of absolute, just need to find the endpoint, find the value of function at the endpoint, find the value of the function at the critical numbers. Okay, so we have to find the critical number if any. So it's going to be x squared minus x plus 1 squared, 1 times x squared minus x plus 1 minus x times the derivative is 2x minus 1. Okay, let's simplify it. Minus 2x squared plus x. Okay. So we will get x squared, x is gone, 1 minus x squared. It's not too bad. That is the numerator. So if we're going to be this 0, x squared should be equal to 1, and x should be plus minus 1. But we are on the interval from 0 to 3. So x equals 1 is a unique critical number in the interval from 0 and 3, okay? So there's only one critical number in the interval, the 2 endpoints. Let's take a look at the value of this. So f of 0 it's clearly it's going to be 0. F of 1, and that's 1 over 1 square minus 1 plus 1, it's going to be 1. F of 3 square minus 3 plus 1. So it's going to be 3 over 7. All you have to do is just compare those 3 values. Okay? And it's obvious this is the absolute minimum value. Okay? And which one is absolute maximum value? This one absolute maximum value. Can you draw the graph? Absolute minimum value. The graph is going up and come here. Okay, so the absolute, if you know the graph, it's easy to tell. But if you don't know the graph, you just compare the 3 different values. 3 values to find the largest one, which is giving the critical. That gives the absolute. Okay. Where's my file? All right, so it's disappeared. So let's draw the picture here. All right, here's a question from book, number 53. The function is going to be x minus x to the 1/3. It is from -1 to 4. Clearly, the function is defined over this interval because x to the 1/3 is defined for any positive number, negative number. But you have to pay attention to x to the 1/3. This one causes you some trouble, right? So this function, first ask yourself, is the function differentiable everywhere in the interval, inside interval? I'm not talking about endpoint. Okay. Well, you just find the derivative first, okay? As pretend it's defined, they're differentiable everywhere. So it's 1 minus 1/3 x to the -2/3. Then you look at this function, this is not defined at 0. Okay, so when x equals 0, 0 to -2/3 is not defined. So that means f prime 0 does not exist. That's okay, it does not exist. The function still continues, right? The function continues and the derivative does not exist when x equals 0. But is there any other critical numbers? Okay, is there any other critical numbers in the interval from -1 to 4? So we have to set this to be 0. Okay, so 1 minus 1/3 x to the -2/3 equals 0. How do you solve it? Well, the idea is that you multiply by this term on both sides, x to the 2/3. So x to the 2/3 minus 1/3 equals 0. Okay, then you move 1/3 to the right hand side and try to get x. You can square both sides step by step, right? Then you find x. X you can plus minus square root of 27. Okay. Anyway, it's a number. It is smaller. It's between. It's symmetric about. They're symmetric about the origin. Right? So you have two numbers. I don't know the value. So this is a critical numbers, right? Critical, yeah, how many critical numbers we're gonna get? We're going to get critical numbers, 3 critical numbers. X equals 0, X equals plus minus. Okay, it can also express in the form 1/3 to the 2/3. Okay, or 3/2. Okay, this is another way to express. Right, we get the critical numbers. The function is continuous on the interval. Right, the function is continuous on this interval. So the function have absolute maximum value, absolute minimum value somewhere. All you have to do is to check the value of the function at the endpoints at the critical numbers. Okay, endpoints. So we have to look at the endpoints. F -1 is going to be -1 minus -1 to the 1/3. It's going to be -1 minus -1, which is going to be 0. Okay, endpoints. Another endpoint. 4 minus 4 to the 1/3. I think this is a greater number. Okay. It's a greater than 0. It's positive number. Yeah. Then you look at the value 0 minus 0 to the 1/3. It's going to be 0 again. How about the other critical numbers? Okay, it's going to be 1/3 to 3/2 minus t is 1/3 3/2 and 1/3, right? You have to simplify this. Minus 1/3 to the 1/2. Is it positive or negative? How can I see that? I think I can take x to the 1/3 out, then get 1/3 minus 1, which is clearly negative. Okay. We also have to look at f negative 1/3, 2/3 here. Okay, because this number is between -1 and 4, right? So it's going to be -1/3 3/2 minus -1/3 3/2 to the 1/3. Okay, so you take a negative sign out, it's plus, and the same idea if you take out 1/3 to the no, this is the 1/3, yeah, 1/2. Okay, this is going to be negative 1/3 plus 1. It's greater than 0. Okay, so let's draw the graph. When x equals -1, I get 0. When x gets 0, I got 0. And this is when x equals 4, it's positive somewhere here. Okay. Yeah, this is a number. Okay, 4, 0, -1. Then you have 2 points here, plus minus 1/3 to the power 3/2. So one side of this is negative when x is positive. Okay, otherwise positive. goes like that. Okay, from this picture, you can tell what is absolute maximum value. F of 4 is the absolute maximum value. Okay, F of 1/3 to the 3/2 is absolute minimum value. We already calculated that, right? It's going to be 1/3 minus 1, which is negative, the absolute minimum value. If this picture is correct, then you also have one local minimum value, one local maximum value. Okay, so F of negative 1/3 is a local maximum value. Okay, and F of negative 1, which is 0, is a local minimum value. So you get more than what we need. So actually we schedule graph almost, right? Now this graph is a picture about the y-axis, about the origin, not the y-axis. Yeah, let's go back to this function, right? The function is going to be x minus x to the 1/3. So this is another function. When you replace x by negative x, okay, it's going to be negative. Takes the negative sign out. Okay, this is going to be negative x minus x to the 1/3. That's going to be negative fx. So f is another function. So if f is another function, if other function, the graph must be symmetric about the origin. So if you can draw the one side, you can draw the other side, symmetric. It's not a surprise. Okay, so y equals f of x is symmetric about the origin. Okay, so if you get the graph, okay, like that, then the other graph must be in the same shape but symmetric about the origin. Okay, symmetry means if you draw the line, if here's this point and the other point must be here. Symmetric about the origin. Okay, let's look at any polynomial. If the powers are odd, then it's symmetric about the origin. So if you draw the one side, you can get the other side. So let's take a quick look about this function 1 plus 1 of x plus 1 of x squared. Okay, x is greater than 0. Okay, so this is an open interval. So we're not talking about closed interval. Okay. So the graph when the function when x approaches 0 from positive side, right, must be positive infinity. Because 1 of x approaches positive infinity, 1 of x squared approaches positive infinity. We also see that x, so this is going to be 1, right? So I'm not sure we have absolute minimum value, absolute maximum value. So the graph looks like that, right? Goes to the infinity, goes here. So I'm not sure it's going down a little bit or just decreasing always. Okay, so we have to find the derivative. It's 0 minus x to negative 2 minus 2x negative 2. Okay, let's find let's see if we can get solutions. Yeah, I'm going to try to get something. So I'm going to change the problem a little bit. Change the sign here. Okay, then I get critical numbers. Okay, so this is when you differentiate this one plus. Okay, so that's a small change. Then the graph will be totally different. When x approaches infinity, function approaches 1. But when x approaches 0, I think the second term determines the sign. Okay, this also should be negative. How do you see that? Because when x getting close to 0, right, I take negative square out. So it's 1 minus x. And this term is positive, okay, getting close to 1. So 1 over x squared, negative 1 over x squared approaches negative infinity. Okay, this is the idea. Okay. So solve this equation. How can you solve this equation? Right? You multiply by x cubed. Each term that's negative x plus 2 equals 0. So clearly x equals 2. When x equals 2, and the derivative is 0. Right? Does the function has a local maximum or local minimum value at this point? Let's look at the f of 2. F of 2 is going to be 1 plus 1 over 2 minus 1 over 2 square. Okay. It's 1 plus a quarter. It's a positive number. All right, so think about it. The function approaches negative infinity and x approaches 0, goes there, right? And somewhere here, the function is positive, right? So the graph passing through this point. Then the limit as x, this is greater than even 1. Yes, but this is going to be y equal, see the function is going to be 1 plus x to negative 1 minus x to negative 2, right? So the limit is 1. So this y equals 1. But there's a value of the function, the value of function at some point is greater than 1. So this is even above this horizontal line. Okay? So this must be the graph. Okay? You know, f of x approaches 1 as x approaches positive infinity. And I know f of 2 is greater than 1. So if you look at this graph, I'm pretty sure from the picture you can have to approaches 1, right? So that means I have to go down. So that means f of 4, f of 2, which is 5 over 4, is absolute maximum value of the function. Okay. Yeah, let me repeat again. So you're given this function, strange function. Okay, you notice that when x approaches 0 from positive side, f of x approaches negative infinity. But on the other side, when x approaches positive infinity, f of x approaches 1. Right? We just don't know how the sketch graph looks like that, right? However, yeah, if you're trying to find the critical numbers, you do find the critical number, x equals 2. You look at the value, f of 2 equals 503. Okay, it's greater than 1. So that means it must go up a little bit and go down. Okay? Because at that particular point, 2, 5 over 2. So that's why you get this picture, and then f of 2 is going to be absolute maximum value. If it otherwise, you cannot tell, you know. Right? So you have to sketch the graph in order to answer the questions. Okay. All right, that's it about today's class.